Hi everyone, we're solving this chemistry paper today. Chemistry paper 49701, paper 41, October, November 2023. The time is 2 hours. We're solving chemistry paper 4 after a long time. I know you've been requesting a lot of Chem P4, but it just takes a long time to make. But I'll be releasing the October, November series as well as a few other paper 4s that I've missed in the past. Before your May June 2024 exam on the 8th of May, I think. So look forward to that. So before we start, let's take a look at the threshold. Quick shout out to my patron, by the way. So currently we have 3 tiers, one for general support, then there's another one for solve papers, notes and requests, where you get access to all my solve papers for chemistry, physics, and bio, paper 1, 2, 4, and 5 for all the past years that I've solved, as well as notes for chemistry and physics, as well as some for math and bio. And you can also request paper solving, which I'll give priority. And for the highest tier, we have the ultimate learning experience, where you get one-on-one video meetings with me via Google Meet. Where we can solve your personal problems, right? Once or twice a month. Less for like 1.5 hours to 2 hours, basically. Plus all the other perks, as well as a shout out at the end of every video on the end screen, basically. So if you need extra support, please do consider supporting me on Patreon. I'll drop a link in the description where you can look into it. You can just support me for a month, get access to the solve papers, the notes just before your exam, and then leave right afterwards when you're done with the exam. Anyway, let's take a look at the threshold. Also, if you do like the content, remember to subscribe to the channel, like the videos, share with your friends. It helps a lot. So for paper 4.1, let's take a look at it. Out of 100, A was at 63, B 57, C 46, D 35, and E at 24. Okay. So out of a full mark of 100, A was at 63, B at 57, 46, 35, and 24. So A star should be at around 70, approximately, because it's 6 marks above this. So around 70, 71, something like that. A star should be around there. Okay, I think we can proceed. Let's start. So I have a bit of the question paper solved. So let's see how long it takes. Starting with Q1. Fluorine reacts with chlorine dioxide, ClO2 as shown. The rate of the reaction is first order with respect to the concentration of fluorine and first order with respect to the concentration of ClO2. So this is the rate equation. Rate is equal to K, fluorine to the power 1, chlorine to the power 1. What does this indicate? If you know the rate equation, you can actually figure out how many of those reactants are involved in the slowest step. So we have 1 molecule of fluorine and 2 molecules of ClO2. So out of those, 1 molecule of fluorine will be involved in the slowest step because we only have 1, and 1 out of the 2 molecules of ClO2 will be involved in the slowest step. No catalyst is involved. Okay. So that's why in the first step, I chose 1 molecule of fluorine and 1 molecule of ClO2. We can't give 2 because if you give 2 here, that would indicate that the power of ClO2 is 2. So you can only give 1. Okay? That's the general idea. So 1 molecule of fluorine, 1 molecule of ClO2. So now you have multiple options. Okay, so this is one option. Another option included, check this, you could also go for this. Fluorine plus ClO2, still 1:1 ratio. That would give you a compound like F2ClO2. I combined everything. F2ClO2. And then in step 2, always remember the product that you formed in step 1 needs to be used in step 2. The intermediate that was formed in step 1 needs to be used in step 2. So we are going to use that again. So F2ClO2, that will react with the remaining ClO2 that I have. That will react with the remaining ClO2 that I have. Okay. Wait up. And that forms the remaining products FC 2 times FClO2. So this is one way, and the other way includes, see, one molecule of fluorine, sorry, one molecule of ClO2. This is the alternate way. Like you can get one product here, one of the FClO2s. I got one of them, and I'm one fluorine atom remains, and then I am going to use this fluorine. Remember I told you a trick, use the product from step 1 in step 2. So I use that with the remaining ClO2 molecule that was not involved in the slowest step to form the other FClO2. But look at, I'm highlighting the difference. Okay, look at this. Our end product is we need two molecules of FClO2, two molecules of FClO2. In the one on the left, in, let's call this method A, and let's call this method B. In method B, I already got one of the products in step 1. That's why I just need the other product in step 2. However, in method B, I did not get one of the products in step 1. That's why I need to get both in step 2. So these are the differences. But one thing remains same. One thing will always remain the same. That is, in the rate equation, since one of them is involved, one of each, right? So I need to use one of each in the slowest step. And usually the slowest step tends to be step 1. Okay, very rarely it's step 2. And so this is same. See, one of each in step 1. And the thing that will remain constant, the other thing is the intermediates might change, but look, the products will remain the same. Two molecules of FClO2. See, 1 plus 2 molecules of FClO2. And remember another thing, you need to use up all the reactants. Look, here I used 2 of the reactants. Here I used 2 of the reactants. And in step 2, I am using the intermediate from step 1, which might differ. And I am using the other molecule of ClO2, chlorine dioxide, which was not involved in the rate equation or the slowest step. Hopefully I could clarify. Okay, now identify the rate determining step in this mechanism. Obviously the first step, because why? We can say that it has the same moles of reactants as orders. It matches same moles of reactants, 1 mole of reactant, and it matches with the order, which is 1 in the rate equation. Or you could say something like this. You could say that it has 1 mole or molecule of fluorine and ClO2, just breaking it down. Okay, just like the rate equation. Yeah. Anyway, when the rate of the reaction is measured in mole per dm cube per second, the numerical value of the rate constant K is 1.22. So write down the rate equation. I already wrote that before. And the overall order is 2, as you know. Or you could just say second order. Why? Because the power is 1, right? So it's just like index form, indices. If you add up the power, 1 plus 1 is 2. So it's second order overall. Now use the rate equation to calculate the rate of the reaction when the concentration of F2 and ClO2 both are 2 into 10 power minus 3. So we know that rate is equal to K into the concentrations. So rate is equal to 1.22 times the concentration of both, which is 1.22 times 2 into 10 to the power minus 3 times 2 into 10 to the power minus 3, or 2 into 10 to the power minus 3 whole square, which is 4.88 times 10 to the power minus 6. Is that fine? Okay. Next, under different conditions and in the presence of a large excess of ClO2, this is a very high yield topic, or a key concept. We could state that as a key concept. So what does this mean? When you have a large excess of something, it is no longer limiting. The rate does not depend on it anymore. So although the rate equation did have 1 molecule or 1 mole of ClO2, since it's in a large excess, we can ignore it completely. So rate completely depends on the concentration of fluorine now, because ClO2 is in a large excess, so its concentration doesn't really matter. It's not limiting. Fluorine, the concentration of fluorine is limiting the rate. Okay, that's the general idea. Okay, so calculate the numerical value of K1 it is given that the half-life of the concentration of fluorine is 4 seconds under these conditions with the unit, and give your answer to 3SF. So we know that before it was a second order reaction, but currently due to the large excess of ClO2, the reaction has been turned into a first order reaction. And we know that for a first order reaction, half-life has a formula of T half is equal to ln 2 or 0.693 by K. So we can actually write that K1, right? K1 is equal to 0.693 divided by the half-life, which is 4 seconds. So this gives us an answer of 0.173 or 1.73 times 10 to the power minus 1. So 0.173 or 1.73 to the power minus 1. And if you look at the unit for first order reaction, you guys know that the unit is found like this. Rate has a unit of mole per dm cube per second always, and fluorine concentration has a unit of mole per dm cube. So if you do the math like this, mole per dm cube per second divided by mole per dm cube, you can get rid of these and you end up with second to the power minus 1. Hopefully that makes sense. Next, an experiment is performed under these conditions, in which, by the way, this formula is only valid for first order reactions, and it is also valid for radioactivity in physics, where K is replaced by the decay constant lambda. Anyway, an experiment is performed under these conditions in which the starting concentration of fluorine is 0.002. Okay, it starts from 0.002. Draw a graph on the grid in figure 1.1 to show how the concentration of fluorine changes over the first 12 seconds. So we know that the half-life is 4 seconds. So after every 4 seconds, the concentration will be halved, okay? So after every 4 seconds, it halves 0.002 to 0.001 after 4 seconds. Then at 8 seconds, it will turn into 0.0005, okay? At 8 seconds, it's 0.0005. And at 12 seconds, it's going to be 0.00025. So since this is 0.0003, so 0.0025 will be somewhere in the middle, somewhere over here, right? Somewhere over here. Yeah, so that's 0.0025 in the middle. So you have to draw this pink line. So draw this pink line according to these points. As you can see, these are the points that I've used. Okay, all good, everything fine. Okay, you draw these. Next, what is asked? Use your graph in figure 1.1 to find the rate of reaction when the concentration of fluorine is 0.001. Show your work on the graph. So we need to draw a tangent at 0.001, which is at 4 seconds. And remember something, guys, when you draw the tangent, make sure that these angles on both sides are more or less the same. Then your answer will be correct, okay? So I drew the tangent and then I took 2 coordinates. I usually extrapolate the line and take the coordinates on the x-axis and y-axis so that one of them is 0. So this is at 0, 0.00164. Every small box is worth 0.00004, right? Because 5 boxes make up 0.0002. So 0.0002 divided by 5 is actually 0.00004. Okay, makes sense? Because look at this, the difference, 0.0018 minus 0.0016 is 0.0002. So if you divide this by 5 boxes, let's do it. 0.0002 by 5 is 4 into 10 power minus 5, which is 0.00004. Okay, makes sense? That's how I got it, 0.00164. And over here, the x-axis is at 9.8 actually, and y-axis is at 0. So after you do the working, there are no powers involved on that side actually. I get a value of minus 1.67 into 10 to the power minus 4. Interesting. So they gave you a range. The range is from, oh, ignore sign. They said ignore the sign. So the magnitude of the gradient is from 1.5 to 2 into 10 to the power minus 4 that was accepted. So yeah, my one falls within the range, and the evidence of the tangent had to be drawn. Okay, that's all. Okay, moving on to question 2. So question 2 was rather tricky. I'll tell you why. How many questions do we have in total? We have 9, so hopefully we'll be done in 1.5 hours. So at first, we are asked to state the expression for Kw, which is H plus times the concentration of OH minus, or an alternate one was, you could go for H3O plus times OH minus, same thing. I prefer the one on the left. Now, this question was a bit tricky. I haven't seen this before. This is the first time I'm facing this. We have two solutions, V and W. V is HCl strong acid, W is NaOH strong base. The concentration of HCl in V is the same as the concentration of NaOH in W. The pH values of V and W differ by exactly 11 at 298 Kelvin. Now calculate the concentration of HCl in V. Okay, I think we can do it. So this is how I did it. In the mark scheme, they actually opted for a slightly different route. I'm not exactly sure what they did. If I do find it out, I'll pin a comment later. Okay. So this is my method of doing it. Okay. It's very complex working, but let's try to figure this out. Come on, say this. So look, we know that HCl is a strong acid, so it dissociates completely. NaOH is a strong base, so it dissociates completely. So we know that the formula for pH is minus log concentration of H plus. So for HCl, I considered the concentration of HCl to be X. I consider the concentration of HCl to be X, so the concentration of NaOH will also be X, okay? So since it dissociates completely, the concentration of H plus will also be X. So we can simply state that pH is equal to minus log X. Okay, pH is equal to minus log X. Next, for NaOH, this is step A. Now step B. So NaOH also completely dissociates. So NaOH forms X moles of NaOH will form X moles of OH minus. And suppose that this X is the concentration, since it's 1 mole per dm³ or something. Okay. Next, we can't do pH here directly. We need to find out the concentration of H plus first. But we do know that the value of Kw at 298 Kelvin is 1 into 10 to the power minus 14, right? So we can write this expression. That's why they stated that on the top. 1 into 10 power minus 14 is equal to the concentration of OH, which is X, times the concentration of H plus. So we get an expression of H plus concentration, which is 1 into 10 power minus 14 by the concentration of OH minus, which also happens to be X. So pH will be minus log 1 into 10 power minus 14 by X. Now the final nail in the coffin. Let's go for it. So we know that the pH values of V and W differ by 11. And clearly, since this is the base, right? Since this is the alkali, it will have higher pH. Okay. So we can write this for step C. Come on, we can write this. We can write pH of NaOH minus pH of HCl, right, is equal to 11. This is the general idea. So pH of NaOH is minus log 1 into 10 to the power right. So minus log 1 into 10 power minus 14 by X. I skipped a step here. It should be minus log X is equal to 11. So afterwards, this turns into a positive sign, right? This one over here, wait. So minus log 1 into 10 to the power minus 14 by X plus log X is equal to 11. And then I just rearrange it, algebra, right? Log X minus this. And then I apply the rule of log A by B. So log A X by B. And after reciprocal, you end up with log X squared by 1 into 10 power minus 14 equals to 11. And yeah, then after algebra, if you solve it properly, let me show you guys if you're weak at this. x square is equal to 1 into 10 power minus 14 into 10 power 11. Then x is equal to root over answer, which will give you x is equal to 0.0316. So that is all. That is all. And that is the concentration of H plus, because I mentioned that before, that the concentration of H plus happens to be X. X is the concentration of H plus. So 0.0316. So that's actually a lot of working for 2 marks. I'm not exactly sure how they did it in the mark scheme. It's a bit different. They just directly wrote pH values of, they just wrote this. pH of HCl is 1.5 and pH of NaOH is 12.5. So since they want the concentration of HCl, so they just went for, we know that pH equals to, well, let me show you what they did. pH equals to minus log base 10 H plus. So they went for 1.5 equals to minus log base 10 H plus. So H plus is equal to 10 to the power minus 1.5, which happens to be 0.0316. This is what they did. Okay. So I'm not exactly sure how they came up with these values with no working. Just with the fact that, their difference is 11. I think I might be missing something over here. So if I do find it out later, I'll let you know. But remember that this method is also valid. It's okay. You're going to get full marks with this. Maybe I'm missing something very simple. So if you guys do find anything out, do let me know in the comments if you have an easier method. And then I'll just pin a comment fixing that, okay? Now, equal volumes of the 2 solutions are mixed. I'm just going to move this working a bit. Wait up. Just going to move this working. One sec. Okay. So equal volumes of the 2 solutions, V and W, are mixed. So yeah, using this, we can actually find out the pH of the 2 solutions, because we know this, right? We know that 1 into 10 to the power minus 14 times 10 to the power 11, root over answer. It's 1 by 1000, basically 1 into 10 to the power minus 3. So root over 1 into 10 to the power minus 3. So that is 0.0316. So we can find out the pH of this solution. So the pH will be minus log base 0.0316. So that is minus, 1 by 1000, root over answer, minus log base 10, answer, that is 1.5. Yeah, so the pH is 1.5 for HCl, and for this one, we know that the pH differs by 11, or you could just do this. pH is equal to minus log base 10, 1 into 10 power minus 14 divided by 0.0316. Use the exact one, or just add 11 with this, right? 11 plus 1.5, same thing. You get 12.5. Anything works. It's up to you guys. So now we have the pH values. Now equal volumes of the 2 solutions are mixed, giving solution X. So hear me out. HCl plus NaOH, neutralization reaction, NaCl plus H2. So this has a concentration of X. This also has a concentration of X. And they will react in the same molar ratio, 1:1. So we're going to get X moles of each. Now, listen. Since the concentration of H plus is equal to the concentration of OH minus, that indicates that the pH will be equal to 7. Because if you solve this according to Kw, you can do this. 1 into 10 power minus 14 is equal to the concentration of H plus whole square. So you actually end up with H plus is equal to 1 into 10 to the power minus 7. And then if you do the math accordingly, if you find out the pH using minus log H plus, you're going to get a value of 7. Okay, understandable? So the pH will be equal to 7, and name solution X. It will be a solution of sodium chloride. You can write NaCl or sodium chloride, anything works. Okay, very good. Now a 1 cm cube sample of what now? HNO3 is added to 100 cm cube of X for mixture Y. A 1 cm cube sample, 1 mole per dl. KOH is added to 100 cm cube of solution X. What is X exactly? Forming mixture Z. Estimate the pH of mixtures Y and Z. No calculations are required. Okay, so this X is actually NaCl. X is NaCl. NaCl is neutral. Okay. Now, KOH, it's a strong alkali. NH3, it's a strong acid. No calculations are required. No calculations are required. Okay. So in general, I can show you using calculation. For example, let's do KOH, right? KOH dissolves to form K plus and OH minus. And look at the moles. Okay, find out the moles. Moles of H plus, OH minus. I think it would be better to use HNO3, right? It would be easier. Wait up. HNO3 dissolves to form H plus and NO3 minus. So find out the moles. 1 by 1000 into 1. 1 by 1000 into 1, which is 1 into 10 power minus 3. That's the moles of H plus. Now it's added to 100 cm cube of this. Okay. Before we had 1 into 10 power minus 7 moles of this. It was the same, but now we have this extra, a lot of H plus. So it's actually negligible. This 1 into 10 power minus 7 is negligible. We can just use this. So just use it. pH is equal to minus log base 10, 1 into 10 to the power minus 3. Oh, but we need to convert it to concentration. Yes. So let's find out the concentration. So the concentration of H plus now will actually be 1 into 10 power minus 3 divided by 100 by 1000. So it's like 0.01. So do it. Minus log base 10, 0.01 minus log base 10 answer. So you're getting an answer of around 2. Okay. So for mixture Y, it's going to be 2. And for KOH, the same thing is going to happen, right? Because it's a strong alkali, the same thing. So since the pH decreased by 5 here, the pH will increase by 5 there as well. Okay, so 7 plus 5 is 12. So since they did not want any calculations, there was a range given. So the ranges are respectively, this one was 1 to 3 and this one was 11 to 13. Okay, that's it. Anyway, let's move on. Suggest the trend in acidity. H2SO4 is a strong acid. Both of these are weak acids. However, the one with chlorine, you know, 2,2 dichloropropanoic acid, right? That is stronger than propanoic acid because of the electron withdrawing effect of chlorine. So let's just state this. I'm writing down the acidity at first. And then we have to say that H2SO4 is a strong acid or is fully dissociated. Okay, that's good. It's a strong acid or fully dissociated. So that's why, there's no comparison. While the others like, propanoic acid, then, 2,2-dichloropropanoic acid, these ones, what about them? Are weak acids or partially dissociated. Yeah. Why don't I just write this down? Wait. One sec. Sorry about this. They are weak acids or partially dissociated. Now we're going to say that the chlorine atom is electron withdrawing or electronegative. So it basically weakens the OH bond. Okay, so it weakens the OH bond. Or you could say that, it stabilizes. So it stabilizes the anion. This is enough, okay, to get full marks. On the other hand, there was an alternate route. You could talk about, sorry, the alkyl group. The alkyl group in, maybe CH3, CH2, COOH actually is electron donating. So it destabilizes. So it destabilizes the anion or strengthens, or strengthens the OH bond. Now you could just add another last thing that, now it's easier or harder to donate the proton. So it is harder to donate proton. And for the upper one, since it weakens the OH bond, so it is easier or it facilitates the release of the proton. Okay? So there are a lot of marking points, but if you write any 4 from these, I wrote 1, 2, 3, strong acid, weak acid, chlorine electron withdrawing, and alkyl group electron donating. These are 4 marking points. And weakening or strengthening the OH bond will be considered as 1 point, and easier or harder to release the proton will be considered as 1 point. So in total there are 6. So you had to give any 4 from these 6. Okay. Now, when concentrated H2SO4 is added to water, a series of acid-base reactions occurs. There are 3 conjugate acid-base pairs that can be identified. Okay. So H2SO4 dissociates in 2 phases when it's added to water. Okay. In the first one, it forms HSO4 minus, and in the second one, it forms It releases the second H to form SO4 2 minus. The first dissociation is stronger. Yeah. Okay. So let's write down the conjugate acid-base pairs. So this is the acid. So this will be the conjugate base. So H2SO4 and HSO4. Similarly here, this is the acid. So this will be the base. HSO4 minus is the acid and SO4 2 minus will be the base. And for the other ones, always look at this. This is the base. H2O is the base since it's added to water. And H3O plus is the acid. Make sense? All good? That's all. Now, the partition coefficient Kpc of a substance Q between hexane and water is 7.84 at 298 Kelvin. Q is more soluble in hexane than it is in water. Okay. So Q tends to be non-polar since it's soluble in hexane more. Define partition coefficient. It is actually the ratio of the concentrations of a solute between 2 immiscible solvents or 2 immiscible liquids is also fine at equilibrium. So 2 immiscible solvents or liquids at equilibrium. Now, 5 grams of Q is shaken with a mixture of 100 cm3 of water and 100 cm3 of hexane at 298 Kelvin and left until there is no further change in concentration. Calculate the mass of Q dissolved in water. So this was very vague, okay? They really did not mention, like, always remember the text. See the text. Kpc of a substance Q between hexane and water. Since hexane comes first, um, hexane will be the numerator. Q will be dissolved in hexane. The concentration of Q in hexane will be the numerator, and the concentration of hexane in water will be the denominator. 7.4 is equal to that. This is the thing that you need to understand. Always follow the text. Yeah, always follow the text. So according to that, I found out that Kpc will be like this. But they were very vague. Like 5 gram of Q is shaken with a mixture of 100 cm of water and 100 cm of hexane at 298 and left there until there is no further change in concentrations. So here, it's actually not mentioned where Q initially was. Like, was Q initially dissolved in hexane or was Q initially dissolved in water? They did not mention anything like that. Like which solution was added later. So you have complete independence. So look at this orange working that I have, this orange working. For this orange working, according to this equation over here, I have assumed that, okay, Q is initially in hexane and then water was added to extract some of it. Okay, so some of it will be removed from hexane, and that part will go into water. And I'm not dividing by the volume because look, both of the volumes are 100, so we don't need to do concentration because the 100 actually cancels out. You don't need to show that. Okay, showing it is not necessary. So yeah, we can say that um, x grams or 0.566 grams of Q dissolved in water after the extraction. Now the alternate route, it could have been like this, right? 5 grams of Q is shaken with a mixture of 100 cm of water. So it could have been like this, like, maybe it was in water in the first place. Maybe it was in water in the first place. Okay. So some of it was extracted to hexane. Some of it was extracted to hexane. And a part of it was removed from the water. So if you solve this accordingly, look, 5 into 7.84 divided by 1 plus 7.84. That gives you an answer of 4.43. So x is equal to 4.43 grams. So that is also an alternate route. Since the question was very vague, you had the option to solve both. Okay. Next, a sample of Q is shaken with a different mixture of water and hexane and left until there is no further change in concentrations. It is found that the mass of Q dissolved in each solvent is the same. Use the Kpc value to suggest possible values for the volume of water used and the volume of hexane used. This is such an important question. I've never seen this before, by the way. This is unique, but it's something that you guys need to understand and figure out. Okay. So any number is accepted in which the volume of water is 7.84 times the volume of hexane. What does this mean? Look, I'll show you. The volume of water needs to be 7.84 times the volume of hexane. Why so? Then they used, what did they say? Allow reverse ratio volume of hexane is 7.4 times the volume of water, which is consistent with D2. In D2, actually, Like, I think this is how Cambridge wanted us to solve the question. Like, sometimes they don't expect candidates to understand that since hexane is written first, it should be on top. Like, this purple working is probably for Kpc is equal to concentration of Q in water by concentration of Q in hexane. And this is the way they wanted us to solve it. Like, Q was initially dissolved in hexane and then shaken with water. So water extracts some of it. That is what they wanted. So here it's not like Q was initially dissolved in the water. It's not like that. It's just that if you use Kpc the other way around, like water by hexane, and then the same thing happens. It was initially in hexane and then water extracted some of it. So that is what they wanted. Okay. So don't misunderstand me. This is what they wanted. Okay. Because I'm seeing in D3 that they wrote something else. So don't worry anyway. So let me clarify this part now. This part is a bit difficult. Let's try to figure this out. Come on. So a sample of Q is shaken with a different mixture of water and hexane and left until there is no further change in concentration. So I want the concentration on top to be the concentration down below. Same. So I want this to happen. 7.84 is equal to concentration of Q in hexane divided by concentration of Q in water. So I want this to be the same. So what do we get? 7.4 is equal to 1. The concentrations will actually cancel out. And check this. It is found that the mass of Q dissolved in each solvent is the same. This is the tricky part. So there is no change in concentration. There is no change in concentration. And the mass is the same. So I actually did something wrong over here. Let me show you. We know that concentration is basically mass of Q divided by like this volume of hexane. And over here it will be mass of Q divided by volume of water. So sorry for cancelling the concentrations out. It's just that the mass of Q will be the same in both, in each solvent. So I can get rid of the masses, and after reciprocal, what do you get? 7.84 is equal to, after reciprocal, right? Volume of water by volume of hexane. So what's remaining? We can say that the volume of H2O will be 7.84 times the volume of hexane. This is what they wrote in the mark scheme. So for example, if I take the volume of hexane to be 10, then the volume of water will be 78.4, because 7.84 times 10 is 78.4. Is this okay? 10 times 7.84 is 78.4. All good? So any other value would work. Like if you took 100 cm cube of hexane, then it would be 784 cm cube of water. Make sense? Now Q is more soluble in hexane than it is in water. It is suggested that Q is one of KCl, sorry. KCl is very polar because it is ionic, it can form hydrogen bonds. So clearly it is not the answer, because I need something that is non-polar to dissolve in hexane. Now check these other two. We have methanoic acid and this compound, which is 4,5 pentan-1-ol, right? So pentan-1-ol and methanoic acid both are actually polar, a bit polar, because both can form hydrogen bonds. But look at pentan-1-ol. Pentan-1-ol actually has a very long non-polar tail. So it is comparatively less polar than the other two. Okay, so that's the logic. All of them are polar, but out of these, pentan-1-ol is the least polar. Or you could say other stuff, like you could go for contains a large non-polar. It contains a large non-polar hydrocarbon chain. Or you could say that it has stronger ID forces with hexane in Q. Okay, makes sense? That's the logic. Anyway, number 3, define entropy. So yeah, go for this. This is the new one, the correct one. Number of possible arrangements of particles or energy in a system. Or the older one is also valid, like it is the measure or degree. It is the measure or degree of disorder or randomness in or of a system, right? Makes sense. Anything works. But go for the newer one, please. This one is better. Number of possible arrangements of particles or energy in a system. Pick the sign of standard entropy change in reaction 1. Okay. So what happens in reaction 1? Two molecules of liquid form one molecule of gas and two molecules of liquid. So clearly, entropy has increased. It's positive because more molecules, more gas molecules in products, more gas molecules or gas particles. Yeah, more gas molecules or particles in products. Or you could say something like, in general, more moles or molecules in products. But the first one is more complete. Okay, because like the molecules could have been solid as well, but the upper one is that's why the upper one is more complete. Now, use the data in table 3.1 to show that the enthalpy change of the reaction is this. So enthalpy change, it is bond breaking minus bond making. So what bonds are broken? These will be positive. So H2O2 is like this, hydrogen peroxide. So one OO single bond and two OH single bonds times 2. So one OO single bond is 150. So that's 150 times 2. And two OH single bonds times 2, which is 4 OH single bonds. Okay, 4 OH single bonds. So these are the bond breaking ones. And bond making, one OO double bond is formed, which is minus 496. And for water, two OH single bonds times 2. 4 into, wait, this should be 4, right? This should be 4. So 4 into 460, like this. 4 into 460. That's that. So you could overall just ignore this because it's the same. You could just go for del H is equal to minus 496 because this one and this one cancels out, right? These two. So you could just ignore them. So you could just go for minus 496 plus 150 into 2. That is minus 196 kilojoule per mole. But I honestly prefer the one on top because it has less chance of error. Okay, next. Use the data given to calculate the standard entropy of oxygen. Okay, so we know that del G equals to del H minus T del S. So del G is minus 238 kilojoule per mole. Del H is also minus 196 kilojoule per mole. And here minus 298 del S. We can find out del S, but it will be in kilojoule per Kelvin per mole. But they want the answer in joule per Kelvin per mole. Okay? This the one for the entropy of oxygen, but we have the change in entropy of the system. Okay, del S. We have del S in kilojoule per Kelvin per mole. Now what you need to do is, you know that the formula for del S system is products minus reactants. So what do we have on the product side? 1 oxygen and 2 H2O. So entropy of oxygen plus 2 times entropy of water, which is 70, minus 2 times entropy of H2O2, which is 102, gives you an answer of the del S, which is plus 141 joule per Kelvin per mole. Okay. And afterwards, or you could just write it as 140.9. That's also fine. And afterwards, you're going to get an answer of 205, or you could go for the exact one, 204.94. If you actually used, 140.9 plus 1, this was 0.1409. That's also fine. It's up to you guys, honestly. Okay. Kilojoule per Kelvin per mole. Okay, that's good. So this is also unique. Like in the same question, we had to find out del S followed by finding out the entropy of one of the reactants, one of the products, sorry. The decomposition of H2O2 is catalyzed by iron 3 chloride and by silver metal. Identify which of these two catalysts is acting as a homogeneous catalyst. So homogeneous catalyst has to be the same state as the reactant. So this is aqueous. So we are going to go for aqueous iron 3 chloride, okay, because it has the same state. Or you could say same phase is also another word as H2O2 or as reactants, okay, anything works. Next, we have electrochemistry. Oh, by the way, you don't have access to the data booklet from 2022 onwards, so be careful. All the data will be provided in the question paper itself, and you'll get access to the periodic table only, okay? An electrochemical cell is constructed with the following half cells: an acidified solution of H2O2, a platinum wire, okay, and chromium 2 plus mixed with chromium 3 plus a platinum wire. Identify the positive half cell, okay. So remember that the positive half cell for an electrochemical cell is the cathode, and cathode is the place where reduction occurs. So since this has a higher reduction potential, the hydrogen peroxide one, so this will be reduced, this will be the cathode, and it will in fact be positive. So the positive half cell will actually be hydrogen peroxide, and E cell will actually be the higher reduction potential minus the smaller reduction potential. So 1.77 minus 0.41. This gives you this answer, okay? All good? Good. Next, calculate the del G. So this is the new formula that is included from 2022 onwards. So I want you guys to go through this properly. Del G equals to minus N E cell F, where del G is the Gibbs free energy change, N is the number of electrons transferred in that equation, E cell is in the standard cell potential, and F is the Faraday constant. Something you have to be wary of is E cell is in volts, so you'll get the answer in joules per mole. You have to convert it to kilojoule per mole later. So del G is equal to, we are dealing with hydrogen peroxide, so 2 electrons were transferred here. So N is 2 moles of electrons. E cell is 2.18 and Faraday constant is 96,500. So you get minus 420,740 joule per mole. So convert it to kilojoule per mole. A lot of rookie students mess this up, okay? So it's minus 420.7 kilojoule per mole, all right? Next. The electrode potential, whereas for 2 electrode reactions are given. Now we're doing with cobalt instead. An electrochemical cell is constructed with the following half cells: an acidified solution of H2 to under standard conditions, so it will be plus 1.77 volts. A solution containing 0.02 mole per dm cube of CO3 plus the oxidized state, and 2 mole per dm cube of CO2 plus the reduced state. So we're going to use the Nernst equation to calculate the value of nu, the new E under these conditions. So you need to memorize the Nernst equation, okay? Which is E is equal to the new electrode potential is equal to the standard electrode potential plus 0.059 by Z log oxidized state by reduced state, okay? So if you follow that, E is equal to the standard electrode potential, which is plus 1.82 plus 0.059 divided by Z, which is the number of electrons transferred, which is 1, log oxidized state CO3 plus, which is 0.020, divided by the reduced state, which is 2. So you get an answer of 1.702. 1.702. Okay, that's all. Plus 1.702 volts. Now we are asked to balance an equation and write it down. So to balance things, the trick is balance the number of electrons first. Okay, so there's 2 on top. I need 2 here, so I just multiply this by 2. So H2O2 plus 2H plus 2E. Oh, by the way, something else. This is very important. Okay, usually this would have been reduced under standard conditions because it has a higher reduction potential. But in the new conditions, under the new conditions, the electrode potential reduces to 1.702, which is actually lower than plus 1.77. So now this will be reduced and now this will be oxidized. Okay, so this will be reduced, so I don't need to switch it up, I don't need to reverse it, but this will be oxidized, so I need to switch it, like reverse it the other way. So cobalt 2 plus will be converted to cobalt 3 plus, and I multiply the equation by 2. So I write this down as per usual, and then I reverse it and write this down, multiply it by 2, get rid of the electrons, and then just copy it down. 2 cobalt 2 plus H2O2 plus 2H plus is equal to 2H2O plus 2 cobalt 3 plus. That's that. Okay, understood? But this was tricky because you had to apply the Nernst equation, figure out that cobalt now has a lower reduction potential than hydrogen peroxide, so it will get oxidized instead, and then write down the proper balanced equation. So it was very tricky indeed. Okay. Next, define standard enthalpy of hydration. So it is the enthalpy change when 1 mole of gaseous ions forms an aqueous solution or dissolves in water. So you could say forms an aqueous solution. Okay. Aluminum fluoride is an ionic solid. Complete and label the energy cycle to show the relationship between enthalpy change, del H sol, del H lat, and del H hydration of the two ions. Okay. Excuse me. So these arrows were not given. So you can start from any way actually. I just chose to copy the mark scheme. So suppose when you write the gaseous ions, they have two routes. Okay. From the gaseous ions, you can either form the ionic compound, which is del H lat, or you could dissolve them directly to form aqueous ions, which is del H hyd. And if you dissolve the solid directly to form aqueous ions, that is actually del H sol. And make sure to draw the arrows properly, write down del H hyd, del H lat, and del H sol properly, and give the state symbols and write down the ions properly. Then that is all. Okay. Then you'll be fine. Is this clear? Understandable? This is a very common Hess cycle that you guys need to face. So do it properly. Okay. Don't mess this up. I really like this Hess cycle. I always give this to my students to test them. Guys, if you do like the content, remember to like the video, subscribe to the channel, share this with your friends. A lot of you haven't subscribed, so that hurts me a lot emotionally. I do this for you guys, so please remember to subscribe. It actually helps with the algorithm a lot, increases the reach. And how do you think my content compares to the content from other channels? Like, I've seen that there are a lot of other people solving chemistry paper 4 and other stuff, but hopefully my content stands out from the rest of them. And if you do support me more or want more of this chemistry paper 4 content, please do comment below. I'll try to solve more for you guys before your exam, okay? Relevant data for this question are given. Okay, let's try to solve this. We know follow the arrows. Okay, this is the detour, this is the direct route. So del H lat plus del H sol equals to del H hyd. So del H lat, which is unknown, plus del H sol, which is minus 209, is equal to del H hyd. So for del H hyd, be careful. Okay, because we have 1 mole of aluminium, which is minus 4690, but 3 moles of fluoride. So that is 3 times minus 506. You need to give the into 3. And after you do the algebra, you get an answer of minus 5999. Okay. Moving on to question 4. Cobalt 2 nitrate CONO32 is a reddish brown crystalline solid. It dissolves in water to form a solution containing COH262 plus complex ions. Complete the table giving the formula. Okay, fine. So we know that cobalt is like when it dissolves with NaOH, it actually forms a blue PPT. The precipitation reaction does not dissolve in excess NaOH and forms COOH2. An alternate was also accepted. You could also go for this COOH2 H2O4, but no charge. That's why it's a precipitate. I prefer the one on the left. An excess of NH3. If you give a few drops of NH3, you would get the blue PPT, but then it dissolves in excess to form a brown solution, which is CONH362 plus, or it gets oxidized, you know, that it gets oxidized. So you could also write CONH36 3 plus. This also works. This is the oxidation product. You know, like how iron 2 plus, the green PPT turns brown over time. So yeah, the same thing happens with cobalt. So you have that option. And an excess of concentrated HCl, it forms the tetrahedral complex COCl4 2 minus, which is actually a blue solution. Okay. So what's the original color of cobalt? It's pink solution, and after you add concentrated HCl, it turns into a blue solution. Yeah. And for copper chloride, it's a yellow solution. Okay. You need to know the colors of copper and cobalt. They are all included in the syllabus. And if you want transition chemistry notes, they're all available on my Patreon. I'll drop a link in the description. The notes are actually insane. They're exam hacks. So you can consider supporting me for a month before your exam. It's just $20 for a month. And then you can just cancel your subscription after you're done with the exam. It would help me a lot and help you guys as well. Calcium nitrate is a white crystalline solid. When heated, it starts to decompose at approximately 500 degrees Celsius. Okay. So yeah, let's break it down. Thermal decomposition of calcium nitrate. It forms this calcium oxide, white solid, a brown gas, 4N2 plus oxygen gas. Suggest temperatures at which MgNO3. Okay, so we know that it's like this: magnesium, calcium, strontium, barium. As you go down the group, thermal stability actually increases. Okay, so calcium is at 500 degrees Celsius. So magnesium would be lower than that, below 500. So something like maybe 400 degrees Celsius, and strontium or barium will be above it. So maybe this is at 600, maybe this is at 700 degrees Celsius. Okay, so something like that. So I would go for this, but they just said this needs to be below 480 degrees Celsius and this needs to be above 520 degrees Celsius. Okay, and what is the explanation behind this? Why does thermal stability increase down the group? We know the drill, right? We know that the ionic radii of the cation actually increases down the group, or alternate answers are radii of Ba2 plus is greater than Mg2 plus, or you could say that I prefer this one actually, that the charge density, the charge density of the cation increases down the group, sorry, decreases down the group, right? This charge remains same. Charge remains the same, but size increases, so charge density decreases. Now, what is the impact? The impact is larger cations, polarize or distort the anion or nitrate list. Very strange. Usually they do not answer in terms of the cation. They usually say that there is less polarization of the anion. For the first time I'm seeing this. Or you could say larger ions weaken NO or NO less, bond less. Okay. Or you could also say there's less polarization of the anion. That's also fine. Okay. We are at 5. We have 5, 6, 7, 8, 9 left. We will be done soon, hopefully. Let's try to hurry. So, why can transition elements behave as catalysts? Because they have more than one stable oxidation state. Why? Due to vacant d orbitals that are energetically accessible. I prefer the first one, but they have also accepted they have vacant d orbitals which can form empty or vacant d orbitals. They have empty or vacant d orbitals that are energetically accessible, or empty or vacant d orbitals that can form data equivalent with the ligands. Yeah. So let's go for this. Silver forms the linear complex AgCN2. Copper forms the tetrahedral complex CuCN4 3-. Titanium forms the complex CiCl4 diars. Diars is a neutral bidentate ligand. State the oxidation number and coordination number of TiCl4. Okay. So this complex has no net charge. So this is neutral. Diars is neutral. And chloride has a charge of -1. 4 of them is -4. So titanium needs to have a charge of +4 to have the net charge as 0. And what is the coordination number? The total number of dative covalent bonds. So 4 dative covalent bonds here, 4 for each monodentate ligand, and 4 here as well because it's a bidentate ligand. 2 times 2 is 4. So in total, 8 dative covalent bonds, 8 coordination number. Draw the 3-dimensional structure of silver and this copper complex. Silver is, linear, so it's going to form a 180-degree bond angle. Make sure to draw the charge, write down the charge. And copper will actually form a tetrahedral complex. Tetrahedral complex, they just drew it like this. Wait up. I'm just gonna shift it a bit. Same thing though, doesn't matter. It's okay. Fine. And the bond angle is 109.5. Since it's tetrahedral, the angle was accepted from 109 to 110. That's fine. And the charge is 3-. Don't forget the charge, okay? Then you'll lose marks. Then we're asked to write down the expression for stability constant for this complex. So according to 2023, this is how they write the stability constant, okay? They use 2 third brackets. 1 third bracket for the complex itself and another third bracket for the concentration, okay? So CuCN4 3-, then a third bracket, because when you form this complex, right? This is the expression for the formation of the complex. 1 copper 2+ combines with 4Cn, yeah? 1 copper 2+ combines with 4Cn to form 1 mole of the complex. So it has no power. And on the other hand, below we have 1 mole of copper and 4 moles of Cn-, yeah? All good? Okay. In a solution of the concentrations of Cn- and CuCN4-, 4 3- are both 0.001. Use the expression from C1 and the value of K step, which is 2 into 10 to the power 27. Yeah, you find out the concentration of Cu2+. Okay, so let's do it. 2 into 10 power 27 is equal to 0.001 divided by a Cn minus concentration is also 0.001 to the power 4 because there are 4 Cn. The power is 4. And we can find out Cu2+, which happens to be 5 into 10 to the power -19. Okay. Next. See, I actually cooked with this paper. This was actually very hard. A lot of key concepts were tested, but I think we can get through it. We haven't started organic yet though. I guess it starts from 7 or something. So we have a piece of a copper containing alloy which has a mass of 0.56 grams. It is dissolved in an acid giving 100 cm³ of a blue solution in which all the copper is present as Cu2+. Now an excess of potassium iodide is added to 25 cm³ of the sample. So out of that 100 cm³, we take 25 cm³ in a conical flask or something and add potassium iodide. All the copper is precipitated as white, CuI. Interesting. Cu2+ ions are the only component in the solution that react with Ki. Fine. Now, the iodine liberated is then titrated with sodium thiosulfate, basically. 0.02 mole per dm³ thiosulfate. This is reaction 2. The titration requires 20.1 cm³ of 0.02 mole per dm³ thiosulfate. Okay, calculate the number of moles of iodine that was reduced in this titration. Okay, let's do that. So moles of thiosulfate is 20.1 by 1K into 0.02, and the molar ratio is half, 1:2. So the moles of iodine will be half the moles of thiosulfate, which is 2.01 into 10 to the power -4. Next, calculate the moles of copper in the original piece of alloy. So if you compare the moles of iodine and copper, you have to multiply it by 2 again because the molar ratio is 1:2. So moles of iodine into 2 But why into 4? Because the iodine was reacted with 25 cm cube of the sample. In the original alloy, it was actually dissolved in 100 cm cube. So this answer, right, 2.01 into 10 power minus 4 into 2, we have to multiply it by 100 by 25 because we took 25 out of 100. So in the original piece of alloy, it will be 4 times that amount, okay, into 4, and then calculate the percentage of copper in the alloy. Okay, so we just multiply by AR to get the mass, and then divide by the total mass of the alloy to get the percentage, which is 18%. Anyway, suggest why solution of copper 2 is colored, but solid CuI is white. So the logic being, to be a transition element to be colored, you need vacant d orbitals. Now the configuration for copper is 4s1 3d10. So if you form Cu plus ion, you only lose an electron from 4s1, but you still have 3d10 electrons. So all the 3d electrons are full. So no promotion of electrons is possible. They can't absorb photons, right? However, Cu2 plus, you actually lose an electron from the 3d orbitals, so it's 3d9. So an electron can be promoted from the lower orbitals to the higher orbitals, okay? So you have to write this down, that Cu2 plus is D9. D9. Okay, let's write this answer again. Wait up. Is D9, or you could say that, in Cu2 plus the D shell or subshell or orbitals are not full, and you need to mention this, that Cu plus is D10, or there you have to say that the D shell or d orbitals are full. D shell is full. That's the general idea. So that's point number 1. And for point number 2, the D to D star, what does that mean? The higher d orbitals transitions, or I'd prefer this, d electron promotion. The d electron promotion is not possible in Cu plus, or you could say that the d electron promotion is possible in Cu2 plus. That's the general idea. Okay, moving on to question 6, 6, 7, 8, 9, last 4. Let's do this. We don't have much left. We'll be done soon, hopefully in 30 minutes. Yeah, 30 minutes or so. Come on, let's hurry. So 5 ligands are listed. State the type. NH3 monodentate, EDTA4 minus is polydentate, CN minus it's monodentate. You need to memorize this, okay? CN minus, Cl minus, NH3, water, all these are monodentate. Then tridentate ligand, this one is new. You have to find out the number of lone pairs from the nitrogens, 3 lone pairs, so it's tridentate. That's why they mentioned it. It's not in our syllabus. We're not supposed to know. And ethane diet and ion, it is also bidentate, okay? Complete table 6.1 using these. They can be used once, more than once, or not at all. We're done. So just the meaning of tridentate ligand. What is it? Oh, you could also say this is hexadentate. Although that was not mentioned here, but they did accept it in the mark scheme. So it's a ligand that donates 3 lone pairs to the central metal atom or ion. Or you could actually go for an alternate answer. You could say something like, it's a ligand that forms. It's a ligand that forms 3 dative bonds to the central metal atom or ion, yeah? So just how this acts as a tridentate ligand, basically you have to refer to the lone pair on each nitrogen atom or amine group is donated. You have to refer to the electrons or the lone pair. Okay. The electrons or the lone pair on each nitrogen atom is donated. Nickel forms the octahedral complex. This complex can exist in 3 isomeric forms. Always remember that the trans isomer will be non-polar because the dipole moments of the water molecules and the EN molecules will cancel out. And the cis isomers will always be polar. So check this. These are the isomers of the nickel complex. So This one is strands because it has completely cancelled out the dipole moments on each side, like this one, this one, this one, and this all cancel out. But look at the cis isomers, which also happen to be optical isomers of each other. They have not cancelled out because look, these dipole moments are not equal to these dipole moments, so they happen to be polar. Okay, good. So describe the difference between cis isomer 1 and cis isomer 2. So both of them are polar, but they are optical isomers of each other, or they form non-superimposable mirror images. They did accept something else, a bit higher level question, like this. They accepted they are enantiomers. They are enantiomers of each other. What do they mean? They rotate. The cis isomers rotate polarized light differently. Okay, so enantiomers rotate polarized light differently. That's that. Understood? Because enantiomers are compounds with similar physical chemical properties. It's just that they have varying biological activity sometimes, and they rotate plane polarized slightly differently. Okay, moving on to question number 7, 8, and 9. Last 3 questions. Let's do this. We got it. So the organic ones, I think they might be easy in this round. Let's see. Okay, what do we have? Sunset yellow. It's an additive used for coloring food. Can you guys cook, by the way? I really want to learn cooking. Hopefully, when I go abroad soon, I need to learn cooking before then. My mom actually makes really good food. So basically, I'm from Bangladesh. I'm a Bengali. So we have really good food. Spices here are insane. You guys should visit here. It's not a good place to visit, honestly. I don't think there are a lot of touristy places. I was actually supposed to go to Japan. I was supposed to be in Japan last week, but didn't happen, sadly. Hopefully next year. Let's see how it goes. I was in Thailand recently for a concert. Might go to Australia soon. So let's see. I have plans to travel a lot more. It's just that I've been so busy with everything, which is why I'm going to let go of tutoring private students here and just focus on YouTube and med school. I'm almost done with med school. I'll be done this year. So I'm a doctor from next year, which is crazy. But yeah, the dream is I'm gonna move to the UK hopefully soon, like within 3 to 4 years. But it's a bit difficult to get into surgery, right? Like medicine is an easier to field to get into, but there are limited seats for surgery, along with discrimination. It's a bit harder since I'm brown. But yeah, my elder brother is also a doctor. He's done with med school, and he gave the licensing exam in the UK. He has the GMC registration. He's gonna move soon. So yeah, both of us are going, but we might move to Australia or Singapore later. We're not sure yet. Let's see how it goes. All right. Guys, make sure you give A2 properly. It's like the most important exam because where you go afterwards depends on this. And if you have good A-level grades, trust me, like everything else will just line up for you. Trust me, all the stars will line up. Anyway, let's focus on this. So molecules E and G contain one SO3- group, which are unchanged in the formation of sunset yellow. So always remember, just go backwards. What group is this, guys? This is called the azo group. It is responsible for the color or the dye. This is the azo group, okay? So let me teach you how it's done. Just go backwards. Look. So always remember the compound with phenol or amine, OH or NH. That one comes later. That one joins with the diazonium salt. So always find out the OH or amine and then just cut it out. From these end sides. Okay, look. The sides of the end. Either cut it here or cut it here. I'm choosing to cut it on the right hand side. Why? Because I know that the OH part will come later. And if it was an NH2, I would also cut it on the right hand side. Okay. So I'm cutting this compound from this part and I'm just going to copy this whole compound over here. That's it. I just copied it. That's the trick. And it will always match. Trust me, guys. Always. All the friggin' time. Always. Okay. So I just cut this out, copied this on the right. You can match the molecular formula. It will match for sure. Okay, good guys. Next. Now for this part, we need to convert it to a diazonium salt now. So just go backwards. This won't be N double bond N anymore. It will be N triple bond N. And remember to give the, N plus on the left hand side carbon, the one with the benzene ring. Yeah. I know this is not the first part. This is part B, but I still like doing it this way. All right. So we have F. You could also just write N2 plus. That's fine. But I prefer this actually. Next. They accepted a lot of things actually for F, but just go for this. This is the better one. Trust me. And what else? We know that the root is from benzene. You have to do nitration, nitrobenzene, using concentration 4, concentration at 355, NO3, 555 degrees Celsius. Then reducing using 10 plus concentrate HCl plus heat under reflux to get aniline. Okay. So then from aniline using HNO2 at temperature less than 10 degrees Celsius, you get the diazonium salt. Yeah. So this step, HNO2, temperature less than 10 degrees Celsius. So the step that comes before, the prerequisite for getting the diazonium salt is an amine or aniline, phenylamine basically. So the step before is the phenylamine. So that's why you just need to convert this N triple bond N plus to NH2. That's it. That's the basic idea. Okay, Mikkel? So if they wanted another step before, you had to give the nitro group instead of NH2. So that's just a trick. Just remember the scheme that I drew and everything will fall into place. Very easy. State the molecular formula of sunset yellow. Let's teach you how to do it. Count the number of carbon. It's very, very straightforward. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 carbons. Then go for sulfur. There are only 2 sulfurs, 2 nitrogens. Look for oxygen. 1, 2, 3, 4, 5, 6, 7 oxygen. Now for hydrogen. Only the ones that don't have anything. Like 1, 2, 3, 4, 5, 6. These are taken up. 7, 8, 9. And then here we have 10. And the net charge is 2 minus due to the SO3 groups. Yeah, straightforward. Hopefully I could clarify for you guys. C16, H10, N2O7 and S2 as well. Suggest the reagents. I already told you that for step 1, we actually need HNO2 at a temperature less than 10 degrees. They accepted less than or equal to 10 degrees. That's fine. And another alternate one is you could also give HCl and NaNO2, which I don't prefer. I just prefer HNO2 because it's much more straightforward, right? HNO2 is formed using this. HNO2 is very, labile or temporary. So you need to prepare it using other reagents. And for step 2, this step, you need to activate the phenol. So it needs to be in alkaline conditions, NaOH aqueous, or you could just say alkaline conditions. That also works, okay? Alkaline conditions. Or else the phenol can't actually react. And if you heat this in water, it will actually decompose to form phenol itself, okay? A phenol compound. Rate the number of peaks in carbon 30 spectrum of sunset yellow. Let's try. Okay, so carbon, only carbon. So this, look at this. This is symmetrical. So you can draw a line of symmetry. So this carbon is unique. This carbon is unique. But look at this. This is symmetrical. So these 2 carbons are the same environment. Then these 2 carbons are the same environment, but this carbon is now unique again. Now this compound over here is clearly not symmetrical, clearly, because this side and this side don't match. So all of these are unique, okay? So this is carbon number 5, unique, carbon number 6, unique, carbon number 7, unique, carbon 8 is also unique, carbon 9 is unique, 10, this is unique. Why? Because look, if you try to draw symmetry, this part has SO3, this part does not. That's why 9 and 10 don't match. Get it? It's not symmetrical, okay? So this is unique 11, then this is unique 12, this is also unique, it's 13, not the same. And finally, on this side, this is 14. So in total, 14 carbons. The one on the left is symmetrical, one on the right is not. So 14 environments in total. Okay, fine. Moving on to the last two questions for the day, 8 and 9. Okay. So number 8, capsaicin. Capsaicin is found in chili peppers. Name all the functional groups present in capsaicin in addition to the CH3O group, which is unreactive. So we have an amide group over here, CONH. We have a phenol over here. And we have an alkene over here. These are the 3 groups that are involved. Okay, great. Oh, they also accepted 14 over here. Okay, good to know. Now, what next? Complete the equation for the reaction of capsaicin with an excess of bromine in the dark. No UV light, so no free radical substitution. So bromine will react in 2 places, okay? It first, since it is phenol, we know that phenol forms a white PPT with bromine, 2,4,6-tribromo-phenol. However, position 2 and 4 are already occupied. So bromine can only get added in position 6. And on the other hand, in this alkene, electrophilic addition will occur. So another bromine will be required there. So in total, we need 2 bromine molecules, one for the phenol, position 6, and one for the alkene. All bromine atoms will be added here from one bromine molecule, and for the other one bromine atom will go here, and due to electrophilic substitution reaction, one molecule of HBr will be released, steamy fumes. Okay, this needs to be balanced. Next, capsaicin is heated with excess hydrogen gas in the presence of platinum metal. So this is a reduction reaction. So we know that hydrogen plus platinum or hydrogen plus nickel in the presence of excess heat can do 2 things. Firstly, it can reduce the alkene to form an alkane. So it reduces the alkene over here to form the alkane, and it can also reduce the aromatic ring to form the aliphatic ring. Like benzene gets converted to cyclohexane. Yeah. So that's the general idea. So the alkene was here initially, now it turned into an alkane. Okay, good. Check if it's fine. I'll check. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, and then the hands. Yes. Okay, I just copied this from here. Okay. Next, when capsaicin is treated with reagent J under suitable conditions, one of the products is methyl propanoic acid. Okay. Methyl propanoic acid. What is methyl propanoic acid? This compound over here. Propanoic acid, and there's a methyl group in carbon 2. They just said methyl propanoic acid rather than 2-methyl propanoic acid because there is no other place to branch out, right? So just methyl propanoic acid. Okay, good. So how did this compound form? If I draw the skeletal compound of this, check this. It's kind of like this. Wait up. So does this seem familiar, this compound idea? Does it match with any place over here? It does. It matches over here. So what actually happened? Oxidative cleavage occurred. And you learned this in AS. If you have 2 alkyl groups, you get a ketone. 1 alkyl group, carboxylic acid. 0 alkyl groups, you get methanoic acid followed by carbon dioxide gas. So since there's only 1 alkyl group connected to this carbon over here, you are going to get a carboxylic acid after oxidative cleavage using hot, concentrated, acidified KMnO4. Okay? Or MnO4 minus, anything works. Okay. Now, what is asked here? There are 3 different peaks in the proton NMR of CH3CH, CH3COH. Okay, I drew the compound over here. Let me do it with you again, yeah? One sec, the eraser is acting up. OneNote is such a bad, app to work on. It's just good to organize stuff, which is why I use it, yeah? Okay, check this. So we are dealing with the proton NMR. So this hydrogen over here will be a singlet. These 2 are the same environment because they have the same thing beside it, and it will be a doublet actually because it has 1 hydrogen in the adjacent carbon And this one will actually be a multiplet because it has 6 hydrogens on the adjacent carbons in total. Yeah. So the COOH, carboxylic acid, will have a chemical shift from 9 to 30, the COH, and it will be a singlet. I told you, because any OH, NH, COOH, all these things, or something like this, CH3CO, all of these will be singlets. OH, COH, NH, remember this trick, okay? All of these will be singlets because they are next to an electronegative atom, or because their adjacent carbon has no hydrogen atom. That's the logic. Okay. Next, I told you that the CH will be a multiplet because its adjacent carbon has 6 hydrogen atoms. Or you could say something like, something like this. It's next to 2 CH3 groups, or you could say it has 6 vicinal protons. It came from the word vicinity. Okay. And the range, the chemical shift, since it's next to, check this, since it's next to a COOH, it will be an alkyl next to CO, and it's like a CH next to CO. So the range will be from 2.2, right? Sorry, it will be from 2.2 to 3. Okay, 2.2 to 3. That's good. Okay. And finally, the CH3 is very basic. It's just alkane. It will be from 0.9 to 1.7, and it will be doublet because one hydrogen and adjacent carbon, or it's just next to CH, or you could say one vicinal proton. Yeah, all good. Okay. Hopefully, I could clarify the splitting pattern, why it happened. And if you guys want a video on spectroscopy, I might release a tutorial soon. So comment down below if you want that. I'll try to release that soon. Capsaicin is heated with excess NaOH. So hot alkali, it is needed for alkaline hydrolysis. What can be hydrolyzed? Ester bonds and amide bonds. So the amide bonds will be broken. And alkaline hydrolysis of an amide, what will it result in? It will result in a salt for the acid part and the amine for the base part. And if it was acidic hydrolysis, we'd get COOH here, acid part, and a salt on the amine part. Okay. So let's go for it. Alkaline hydrolysis, careful. So the amine will remain amine. An alkali cannot react with an alkali, okay? So we break this down and this turns into NH2. And remember, phenol is also an acid. So it will react with the alkali to form NaO. This is very important, okay? On the other hand, the amide does form a carboxylic acid. However, since the carboxylic acid is also acidic in nature, it will react with the alkali to form a salt. So that's the general idea. So you need to break the amide, form the amine, and the phenol and carboxylic acid need to react with the alkali to form salts. Okay, important. So name the 2 types of reactions occurring. So clearly hydrolysis, and over there neutralization or acid base. Okay. Next, we react with a strong reducing agent LiAlH4. Where will this actually react? So LiAlH4 cannot reduce the benzene ring or the alkene. However, what can LiAlH4 reduce? Remember, in general, carbonyl. LiAlH4 can reduce ketone, aldehyde, carboxylic acid, ester, amide, nitrile. These are the ones that LiAlH4 can reduce. Ketone to secondary alcohol, carboxylic acid to primary alcohol, aldehyde to primary alcohol, nitriles and amides to amines, and esters to secondary alcohols. Okay, so the amide, this amide will just get reduced to form an amine. That's it. LiAlH4 can do that. Just remember that draw the same compound. It's just that this part over here, this part will disappear. That's the end result for an amide. Reduction of an amide to this secondary amine. That's the role of the LiAlH4. Okay, remember that. Okay, moving on to question number 9, last one for the day, 13 marks. We will be done soon. Let's go for it. Draw the intermediate compound M in the box. Benzoyl chloride can be made from ethyl benzene in a 2-step process. Okay. So to convert anything to an acyl chloride, we need a carboxylic acid first, right? So we will just convert it to an carboxylic acid. So oxidizing the side chain using KNO4 is a possibility, right? So what are the conditions? From 2022, the condition has been changed to hot alkaline KMNO4, or you can just go for MNO4 minus ions, hot alkaline MNO4. And to convert carboxylic acid to acyl chloride, remember three things: either thionyl chloride, PCl5, SOCl2, or you could go for PCl3, but then you need to mention heat. Okay, identify the type of reaction 1 and 2. Easy. One is simply oxidation of the side chain. Regardless of the length of the chain, it will always be benzoic acid. And step 2 is actually, remember, a nucleophilic substitution reaction. So nucleophilic was optional, but remember the reactions of alcohol with PCl5, PCl3 and heat, SOCl2 and others, HX in general, and also carboxylic acid, all of these are actually nucleophilic substitution reactions. Nucleophilic substitution is a characteristic reaction of alkyl halides and alcohols and carboxylic acids. Okay? Okay. Moving on to the last part. Okay. So the new addition to the syllabus from 2022, acyl chlorides, very high yield. This addition elimination reaction was added in 2022, and since then it has been a staple. It has always been coming in A2. Okay, so it's a characteristic reaction for acyl chlorides. Let's go for it. Come on. Complete the mechanism, include all relative dipoles and charges, all relevant lone pairs, curly arrows, and the formula of the second product in box 3. So let's begin. Okay, so firstly, there will be an attack. An acyl chloride can react with phenol to form an ester. Okay, phenol can form esters with acyl chlorides only, not carboxylic acids. So you draw the lone pair. Now this lone pair will actually attack this carbon because due to the presence of this oxygen, a dipole exists over here. Okay, there is a dipole over here due to the electronegative oxygen, which is why this lone pair from oxygen will attack the carbon. Okay, so that is step 1. Attack of the lone pair of the nucleophile on the electropositive carbon atom. However, this carbon will then get 5 bonds, which is not possible, right? So we have to sacrifice one bond over here. So heterolytic fission of that bond occurs. So one sigma bond is formed and one pi bond is broken. Next, in the intermediate, let's look over here what happened. Our intermediate, this oxygen over here, actually has a negative charge because it has undergone heterolytic fission. And on the other hand, this oxygen over here has a positive charge because it sacrificed one of its electrons to give to carbon because its one was taken away by this oxygen over here. Okay, so these are the charges. Now what will happen? So basically heterolytic fission will occur again. This chlorine will take away the electron from carbon. Okay, so now the double bond can reform again. The pi bond can reform again from this negative oxygen. And we need to fix this deficiency over here. So who makes the final sacrifice? This hydrogen over here. Okay, this hydrogen, another heterolytic fission will occur, and hydrogen will release its electron to oxygen so that the charge is fixed. So the pi bond reforms, sigma bond breaks, and the hydrogen, this sigma bond also breaks. The hydrogen releases its electron to this oxygen. So what is released in the process? 1 Cl minus and 1 H plus from down below. So as a result, we actually get steamy fumes of HCl. Always acyl chlorides will always form HCl. There were 10 marking points in total. Okay, 10 marking points in total. Just follow me, follow how I did it, and then everything will be fine. Okay, the mark scheme is given properly. You can check that, but just follow my method, then it will be fine. And the name of this mechanism is, you can add this, this is optional, nucleophilic. This is not main, but mainly it is addition elimination. That is all, folks. Moving on to the last one for the day, which is the ease of hydrolysis of, what do we have? What do we have over here? Benzoyl chloride, C6H5. COCl, benzoyl chloride. Then we have chloroethane, CH3CH2Cl, chloroethane, and chlorobenzene, just chlorobenzene. Okay. All right, fine. So the answer to this is a very straightforward actually. Then each compound is added separately to water. Fine. So let's do this. Okay, so the easiest to hydrolyze will actually be benzoyl chloride. I'll tell you why. And the hardest will actually be chlorobenzene. And in the middle, we have chloroethane. Let's see why, okay? So in general, for chlorobenzene, I'm talking about chlorobenzene now. In chlorobenzene, the lone pair actually overlaps with the delocalized system. So we can say that the lone pair on chlorine overlaps or is delocalized with ring, into ring, or it is incorporated with the ring. So it has a partial double bond characteristic. Okay, so this is another marking point. So this strengthens the CCl bond, or you could say that it has a partial double bond characteristic, or it is more difficult to break. Okay, anything works. I'm not writing those, but you could say that this strengthens the CCl bond, it has a partial double bond characteristic, or it is more difficult to break. Same marking point. Okay, next. For chloroethane, what happens? The positive inductive effect of the alkyl group what does it do? We have to link it. Okay. So remember always, like, if you donate electrons, what happens? It strengthens the bond. But this strengthening is still less than chlorobenzene. Okay, we can write that. But less strengthening. Okay. But less strengthening than chlorobenzene. This was not mentioned in the mark scheme. I'm just saying this to make you guys understand. Okay. And finally, last but not least, what happens in benzoyl chloride? Mainly, this carbon is the most electron deficient. Why? Due to the fact that it has two electronegative atoms. In benzoyl chloride, we can say that the C of CCl is most electron deficient. Or you could say that it has an electronegative oxygen atom. Or you could talk about the CO group, electron withdrawing. You could talk about it has an electron withdrawing CO group. It has an electron withdrawing CO group. So this weakens the CCl bond, so it is very easy to break. So hopefully that's it. I could make you understand. So to get full marks, just write this and any 2 marking points from below. So this chlorobenzene 1, chloroethane, benzochloride, these are unique points, and strengthening or weakening will be considered as 1 point. So you don't need to repeat it, okay? So guys, hopefully that was it. CAI did cook with this paper. It was extremely hard. So hopefully I could clarify each and every concept except the first part in question 2, where there might have been an easier way to approach the question. So if you guys do find it out, please let me know. I'll then pin it in the comment section. Anyway, thank you for tuning in, and hopefully this content helped. If you did like it, please remember to subscribe to the channel, hit the like button, and share this with your friends, and consider supporting me on Patreon. So quick shout out to my top tier patrons for the month. As usual, we have Dewa, the complete chat, supporting me from the very beginning, and Tim, who has recently joined the highest tier, where you get access to one-on-one meetings with me once or twice a month, where we solve your personal problems for like 2 hours or so, for just $50 a month, which is a steal, I think. So if you have any final problems, you can talk to me about it before the exam. And yeah, I'll just link the paper for 9701, October, November 2023, 4-2 up here when I solve that, and the paper for 9701, May, June 2023, paper 4-1, or May, June 2023, paper 4-3 down here when I solve that, and the playlist for chemistry, paper 4 up here. And remember to hit the subscribe button. See you guys. Bye bye. Also, this paper is the same as October, November 2023, paper 4-3. It's the same paper, alright? See you guys. Tata.